Hello, welcome to 2-4 lesson B. In this example, we're going to build off of what we talked about in 2-4 lesson A, the limit definition of a derivative. In this video, we're going to specifically look at examples and how to find a derivative using the limit definition. So let's go ahead, let's dive right into some examples. Here, just a recap. We have the limit definition, right? So to take a derivative, you take the limit of f of x plus delta x minus f of x. Again, in the numerator, what you have, this is your delta y, your change in your y values, divided by the delta x. Okay, and we want that delta x to go to 0, right? I want to take the secant line and I want to reduce it to where it touches the graph and it's equal to that tangent line, right? Which is what we've determined is the derivative. So if f of x is equal to x squared plus 2, find f prime of x. Okay, so what we're going to do, again, I'm going to plug in f of x plus delta x here into my function. So wherever I see my x value, I'm just going to plug that in, okay? And this is what we get. So we get x plus delta x quantity squared plus 2, okay, minus f of x. Now when I drop in f of x, I'm going to use parentheses. You got to protect that because you're going to have to distribute that negative. So then I have x squared plus 2, okay, and again this is all over delta x. Okay, so what I'm going to do, I'm going to write the next line is equal to the limit of delta x going to 0. What I have to do is I have to expand my numerator. So if I go ahead and multiply this out, we get x squared plus 2 delta x plus delta x squared plus 2 minus x squared minus 2. Okay, so lots of algebra going on here. And what's going to happen is you will have factors reduce or cancel out. Okay, so notice I have an x squared term that cancels here, right? Positive and negative, and I have a 2 that cancels. Okay, so what we end up getting, the limit. Computer's freaking out. The limit as delta x approaches 0 of what we get is 2 delta x plus delta x quantity squared over delta x. Okay, so now if I take the limit, right? I can't take the limit. I can't just plug in 0 because my delta x is in the denominator, and that would give me a denominator 0. So I cannot do that. Right, so the trick here is to factor that out. So take the limit as delta x goes to 0. And notice I'm going to factor out a delta x from here and 1 from here. Okay, and so when I do this, I get 2 plus delta x all over delta x. Okay, and lo and behold, what do you notice? Delta x cancels. And we get this, the limit as delta x approaches 0 of 2 plus delta x, the denominator, okay. And then now I can go ahead and I can evaluate this limit since this is a polynomial and it's continuous everywhere. So what this is, right, if I just evaluate at 0 is, oh, I dropped my 2x, okay, it gives us 2x. So where did this x come from? Up here. So I made a boo-boo. So I have x plus delta x times x plus delta x. So when you do this, right, we get our x squared, and then x times delta x is 2x delta x. Okay, so I'm just going to go back in here. I'm going to factor in this, drop in this 2x. Right? Okay, so we get 2x. So therefore, the derivative for this function is 2x. Okay. Part B, it says use your answer from part A to find f prime of 3. Well, I know that f prime, right, of x is equal to 2x. So in order to find f prime of 3, all we do is evaluate. So 2 times 3 is 6. Good job. You got it. Okay. So that's finding the derivative, right? Okay, is 6. Good. All right, moving on. Looking at, here we go. Problem number 2. So number 2, again, we're going to use the same limit definition. Okay, and I'm just going to go ahead and I'm going to find y prime. And what I'm going to do, I'm going to switch it up. Instead of using the limit of delta x, I'm just going to say the limit as h goes to 0 of f of x plus h minus f of x. Okay, all over h. So this is just one of the different definitions. So I'm going to use this one. Okay, and what we get is the limit as h goes to 0. And I'm going to drop in my function. So I have the square root of x plus h minus the square root of x all over h. Okay, and I want to go ahead and I want to take the limit as h goes to 0. However, notice again, I have the h in the denominator. If that's 0, I can't divide by 0. So what do? Well, what we're going to do is we're going to multiply by the conjugate. I'm going to multiply, and you should remember this from Math 3. We did problems just like this. I'm going to multiply by the conjugate, top and bottom. Okay, so I get square root of x plus h plus the square root of x. Okay, multiply by that top and bottom. Okay, and so what does this give us? Well, this gives us the limit as h goes to 0. Okay, so I'm going to multiply my terms. So on the top we get x plus h. Okay. Plus, we're going to get here middle terms, right, that are going to cancel out. So that's why we do this. So, well, I'll just show you. So root x times root x plus h, right? And then our second term is going to be a minus root x times root x plus h, okay, minus x. Okay, all over. And in the denominator, we have h times our radical. So x plus h plus root x. Okay. So what we'll do here is we'll simplify. Again, notice that these terms cancel. Okay. And here I have an x and then a negative x that cancels. Okay. So we get the limit as h approaches 0 of h over h times the square root of x plus h plus the square root of x. Okay, so what happens now? Well, again, h's cancel. And we get the limit as h approaches 0 of 1 over the square root of x plus h plus the square root of x. Okay, all right, we're good. So now if I want to evaluate this limit, I can go ahead and do this. I can plug in 0 and I get the limit as h goes to 0 of 1 over square root of x plus square root of x, which is 2 square root of x. Sorry, I already did this. I don't need this. This is just equal to 1 over root x plus root x, which equals 1 over 2 root x. Okay, and there is your derivative. All right. Okay, so there's example 2, and here is example 3. So what we're going to go ahead and do, we'll use the same limit definition. Okay, so here, given y equals f of t equals 2 over t, find the derivative of y with respect to t. So all they're doing is they're substituting out the variable x, and now we're going to use t. Oftentimes this is used when we're talking about like time, real-world contextual problems. So they talk about time. So here, dy dt, which is the same thing as f prime of t, well, this is equal to the limit as h goes to 0 of, and again, I'm going to plug in my function f of t plus h, so 2 over t plus h, okay, minus f of t, which is 2 over t, okay, all over h. So I want to take the limit, same problem, I can't plug in 0 into my denominator, so I have to kind of go ahead and reduce this. The trick when you have these fractions in your numerator, you're going to go ahead and multiply by the lowest common denominator, okay? And so in this case, what I'm going to do is I'm going to multiply by t times t plus h over t times t plus h. Okay, and what happens when we do this, we'll get a common denominator. Okay, or actually the denominators will cancel likewise, right? So if I multiply by this times every single term, here the t plus h cancels, and I have a leftover t. Okay, so I have 2t, and then when I multiply here, right, the t cancels, and I have t plus h left over. Okay, so minus 2 times t plus h. And all of this is over h times t plus h. Okay? So what we're going to do here, I'm going to go ahead and kind of multiply this out so we can see, okay, what cancels, what reduces, and we have 2t minus 2t, hey, there you go, plus 2h all over h times t plus h. Okay, so you should notice right away, right, the 2t's cancel, and we get the limit as h goes to 0 of 2h over h times t plus h. Okay, and our h's cancel, and we get 2 over t times t plus h. Okay, oh, and this is the limit as h goes to 0. I know it's very annoying to rewrite this limit as h goes to 0 every single time, but we have to go ahead and include that. Okay, otherwise it wouldn't be equivalent, right? So I have it, and what I'm going to do now, I'm going to go ahead and evaluate the limit at 0. Okay, so I mean, what happens is in the numerator I have 2. In my denominator, we have t times t plus 0, which ends up being 2t squared. Okay, so there we go. Except I just noticed this is negative Schorberg, so that made this negative. It should also make this negative as well, which would make this negative, which would make this negative, which makes this negative. Man, so much algebra I'm making mistakes, slipping. Okay, so here is our derivative. So this is dy dt. Okay, and there you have it. So in this video we looked at, we looked at examples of using the limit definition. A lot of algebraic magic that we're doing here, manipulating these functions to cancel out, to be able to take the limit, and there you have it. So there's examples. The next video we'll look at using the alternate definition of the the derivative. Catch you next time.